Hello, this is yet another video on exploring the eigenvalue problem. We're going to ask a few questions around it and not just explain a way of solving an eigenvalue problem. The matrix we're going to work with is the following. So consider the matrix A. It will be a 2 by 2 matrix given by 5, 1 in the first row and 1 and 5 in the second row. What we want to do is to find all possible eigenvalues and eigenvectors for this matrix. Alright, so let's just remind ourselves what does that mean. The eigenvalue problem states it requires one to find all possible solutions of this matrix equation, where lambda is a scalar and k is a column vector, and then lambda is called an eigenvalue, and provided k is non-zero, lambda is called an eigenvalue when there is a non-zero k, and when such k exists, that k is called an eigenvector. The method that I now assume that you're familiar with, so I'm not going to go into details there, consists in writing down first of all the auxiliary equation, which is the determinant of a minus lambda I equal to 0, and solving the auxiliary equation. Solutions of this equation are going to be exactly the eigenvalues for the matrix. And then using each of the eigenvalues we find, we can get the eigenvectors by solving the this matrix equation, which then can be written out as a system of linear equations. Okay, so what is the matrix A minus lambda I when A is the given matrix? Okay, so that's A, and then we have to do minus. I is the identity matrix, so it's 1, 0, 0, 1. And when we subtract these two, well, first of all, we multiply lambda in there, so we get 5, 1, 1, 5, and then minus from that, minus lambda, well, plus, sorry, minus from that, lambda 0, 0 lambda, and that gives us 5 minus lambda, 1, 1, 5 minus lambda. So the matrix we get here, the matrix that's going to be used for the determinant, is just the matrix A with lambda being subtracted from its diagonal entries. Okay, great. Now let's see what is the determinant of that matrix. So the determinant of that matrix, 5 minus lambda, 1, 1, 5 minus lambda, is 5 minus lambda squared minus 1, which is equal to lambda squared minus 10 lambda plus 25 minus 1, and that's equal to lambda squared plus, sorry, minus 10 lambda plus 24. This is the determinant of the matrix, and then the auxiliary equation will be given by equating this to 0, and we want to solve this equation because eigenvalues are exactly solutions of this equation, so we want to solve this equation. However, if you notice that I became silent for a while in writing these equalities out, what happened there is that I realized that we should actually not do this simplification. The simplification we did here is not really going to be helpful. Well, it will be helpful for seeing explicitly what the auxiliary equation is, but it will not be so helpful in solving it. It is much better, in a particular case of the expression being of this form, to decompose this as 5 minus lambda minus 1 times 5 minus lambda plus 1. And then the auxiliary equation becomes 4 minus lambda times 6 minus lambda equals 0. So you see, we have now it written in such a form that the solution of this is immediate. Of course, we could have also worked this from the previous line, but it was not really necessary to go through all these three equations when we could have gotten to the answer straight away. And so, by the way, that's a hint to take into account, especially with 3x3 matrices, working out the characteristic equation. Have I been calling this auxiliary equation? I meant to say characteristic equation. So working out the characteristic equation, very often, especially with symmetric matrices, you can simplify the expression in such a way that the solutions will come out directly instead of multiplying everything out and then trying to solve the cubic equation that you will get in the case of a 3x3 matrix. Okay, so let's go back to our auxiliary equation where the solutions are lambda equals to 4 and lambda equals to 6. So then this means that 4 and 6 are the eigenvalues for the matrix we are working with. The matrix being A equals 5, 1, 1, 5. So these are the eigenvalues for this matrix. Great, we found the eigenvalues, but that doesn't mean that we know what the eigenvectors are yet. To find the eigenvectors, we want to put these eigenvalues back into the matrix equation. And in fact, what we want to do is to write down a system of linear equations from the matrix whose determinant we took. So the vectors k that satisfy ak equals lambda k will be exactly those vectors. In this case, they're column vectors of height 2, because we're working with a 2x2 matrix. There will be exactly those k1, k2s that make the following system, that solve the following system: 5 minus lambda k1 plus... Okay, before I write this down, let me explain where I'm getting it from. So remember, the determinant involved in the characteristic equation had the matrix 5 minus lambda 1, 1, 5 minus lambda. So this is the matrix A minus lambda I. And what we want now is to write down the corresponding system of equations. And so I'm writing a system of equations corresponding whose coefficient matrix basically is this matrix. So that will be 5 minus lambda k1 plus 1 times k2 equals 0. And the second equation will be 1 times k1 plus 5 minus lambda k2 equals 0. The whole point is that this system is equivalent to that thing there. And you can work it out if you don't already know this from the theory, that these things are equivalent. You just write this matrix equation out in terms of the terms, the entries of the matrices, and then you see, you compare the two things. You first multiply A by K, of course, you compare the two things, and you see that if you move lambda K on the other side, and write those equality of the two column vectors, you get there term by term, you will get this system of linear equations. So eigenvectors k for the eigenvalue lambda will be those column vectors consisting of the entries k1 and k2, such that the k1 and the k2 are solutions of the system of linear equations. Okay, so what we want now is to solve the system of linear equations for each of the eigenvalues that we found. We have two eigenvalues at hand. These are lambda equals 4 and lambda equals to 6. And so each of them we'll have to look at separately, and then in each case get the corresponding eigenvectors. Let's start with the eigenvalue lambda equals to 4. When lambda equals to 4, if I put this into the system, I'm going to get k1. So because 5 minus 4 is 1, so it's going to be k1. And then I have plus k2 equals 0. And in the second line, I'm going to have k1 plus, so putting 4 there gives 5 minus 4, which is 1. So it's again k1 plus k2 equals 0. Okay, so the two equalities here in the system are equivalent, of course. So we can safely disregard the other one. It's not going to play any role. and just from the first one then we can extract that K1 must be equal to minus K2. So we can write down its solutions in the form some K as my K2 and K1 being minus that, so it's minus K. So this is a small k and the other one is a capital K, where K is allowed to be any real number as long as it's not 0. Why cannot K be 0? Because I hope I didn't forget to mention that when I was recalling the eigenvalue problem, because an eigenvector is not allowed to be the 0 vector. Okay, so eigenvectors are all possible solutions of this equation which are not the 0 vector. 0 vector obviously is always a solution of this thing, right? Okay, and yeah, now I remember I didn't forget to say that. And so we proceed. For lambda equals 4, we have found the eigenvectors. We can even represent the whole eigenspace, which is the set of all eigenvectors together with the 0 vector included in the set, but not counting as the eigenvector. So we can represent the whole eigenspace as the span of a single vector, and namely we just pick one such vector by picking any value for k. For simplicity, let's pick k equals 1, so we'll have minus 1, 1, and so this single eigenvector now represents all of them, because all the other eigenvectors can be obtained from this one by multiplying that vector with a non-zero scalar. And so sometimes in a case like this, one says that there is one eigenvector, where one doesn't really mean that it's literally one, but just that the eigenspace is spanned by one eigenvector. Okay, all of this is for the eigenvalue lambda equals to 4. We still have to work out what the eigenvalues are for lambda equals to 6. So let's have a look at that. When lambda equals to 6, so the first thing we're going to do, of course, just as we did before, we're going to put this value into the system. Let's copy the system out. So this was the system we had, and let us put it in here in the new slide, and then maybe somewhere in the corner there, and then we want to substitute in there lambda equals 6. I wanted to erase that little thing there, but doesn't work. There we go, this should work. Okay, we don't need that little white thing there. Great. So with lambda equals 6 inserted into this system, we're going to get the following system. 5 minus 6 is minus 1, of course, so it's minus k1 plus k2 equals 0. That's the first equality. And then the second equality, we have k1 plus 5 minus 6 is again minus 1, so it's actually minus k2 equals 0. And what we can see here is that the two equalities are actually equivalent to each other, just as before. One can be obtained by multiplying the other one by minus 1. So the other one is not going to give us any new information or any further restrictions. And so the solution of this system is given by all possible k's in the form, okay, so let's complete this line here and write down that k1 is equal to k2. So it could be all possible vectors of this form, where the k, once again, can be any real number except 0, because the 0 vector is not allowed to be the eigenvector. And just as before, we can write out the whole eigenspace here as a span of a single vector, which is 1, 1. Okay, so that completes the investigation. And let me just maybe add, just as before, what we did that in the orange there, we could present the answer just by a single eigenvector for the eigenvalue lambda equals to 6. So we could just say that for that eigenvalue, this is the eigenvector, with this meaning that all scalar multiples of that will also be eigenvector. Since from the theory we know that eigenvectors for a given eigenvalue always form, once we add 0 to it, always form an eigenspace. In other words, always form a subspace. If we give a few eigenvectors and we say that, okay, these are all, of course they're not all, they're just the key representatives in the sense that they are the basis for the entire eigenspace. Okay, so we can then summarize the investigation as follows. There are, for the matrix A, there are 2 eigenvalues, lambda equals to, was it 4 that we had before? I think it was 4. There we go, yes. Lambda equals 4, and for that we have the eigenvector minus 1, 1, which means whole infinitely many of them, obtained by multiplying this by any non-zero scalar. And we also have another eigenvalue equals 6, for which the eigenvector is given by this representative. Great. That completes solving the eigenvalue problem we had originally, and what we want to do now is to ask a few questions that could be very easily derived, the answers to which can be very easily derived from having solved the eigenvalue problem. So the first question is the following. Is the matrix A singular? What does it mean for a matrix to be singular? Well, a matrix is singular when its determinant is 0, or another way to say it is to say that it is invertible. So, sorry, that it's not invertible. It does not. The inverse does not exist. So the E here, the turnaround E, is a mathematical way of saying something exists, and I've just crossed it out to mean that something does not exist. So a matrix is singular when it is not invertible, when it doesn't have an inverse, or in other words, which is equivalent when its determinant is 0. The thing is that we can write down A as A minus 0 times I, you see? And so determinant of A being 0 then means this determinant being 0. But of course, this is the same as to say that 0 is an eigenvalue. So a matrix is singular when it has an eigenvalue equal to 0. And here we see an important information that eigenvalues provide about the matrix. Surely whether the matrix is invertible or not is important, and so eigenvalues can actually detect that. In the current case, we had only 2 eigenvalues and none of them were 0. So then we can say that the matrix isn't singular, because if it was, then it would have a 0 eigenvalue. So the answer to the question whether the matrix is singular or not is no, because A does not have eigenvalue equal to 0. Great. Another question, which is of a similar form, we want to extract some additional information from solving the eigenvalue problem, is the following. Okay, so now that we know that the matrix isn't singular, it means that it has an inverse, right? So remember, a matrix was supposed to be singular when there is no inverse, so not singular means that there is an inverse. And so if the matrix has an inverse, then we can ask the question, what are eigenvalues and eigenvectors for the inverse matrix? And it turns out, so let's actually formulate this question. what are eigenvalues of the inverse matrix? And it turns out this is a general fact that's true for all arbitrary square matrices that are not singular, that the eigenvalues of the inverse are exactly the inverses of the eigenvalues of the original matrix. So the answer here is lambda equals, well, before we had 4 and 6, and so here we'll have 1 over 4. So when I said inverses, of course, what I meant was, maybe I should call them lambda 1 and lambda 2, 1 over 4 and 1 over 6, because these are the multiplicative inverses of 4 and 6. And I should perhaps keep that style here as well. There are two eigenvalues, lambda 1 and lambda 2, otherwise it seems like 4 will be equal to 6 because they're both equal to lambda. Okay, so if we want to know what the eigenvalues of the inverse matrix are, it's sufficient to take the eigenvalues of the original matrix and just take their reciprocals. You see, we don't even have to compute the inverse matrix to find its eigenvalues once we know what the eigenvalues of the original matrix are. What about the eigenvectors? Well, again, it's a general fact that the eigenvectors will be the same as for the original matrix, and they will correspond to the same eigenvalues. So for lambda equals 1 over 4, the eigenvector will be minus 1, 1, and because that was the eigenvector for lambda equals to 4, so that will be the same eigenvector, and all of its scalar multiples as well, of course. And for the eigenvalue lambda equals to 1 over 6, the eigenvector will be 1, 1, because that was the eigenvector for lambda equals 6. Now, what I want to say is just to make one more remark, how we can intuitively see that what I described to you is indeed valid. So there is a certain intuition about matrices being linear maps. They transform vectors into other vectors in the same space. The eigenvalue then represents a factor by which a certain vector, the eigenvector, gets stretched as a result of transformation. And the inverse matrix is the inverse transformation. So now you see, if I have a transformation that stretches, for instance, this vector by a factor 4, then the inverse of this transformation will stretch the same vector by a factor 1 over 4, because the inverse is supposed to recover back what where we originally started with. And the same works for the second vector. So if A stretches this vector by factor 6, then the inverse of A, which is the inverse procedure to stretching by factor 6, and of course the inverse procedure to that is stretching the same vector by 1 over 6. So that's how you can see intuitively, by means of linear maps, that the that 1 over 4 will be an eigenvalue for the inverse of A when 4 is an eigenvalue for A, and the same for 1 over 6 being the eigenvalue for inverse of A when 6 is the eigenvalue for A, and the eigenvectors for the inverse matrix for the corresponding for each corresponding eigenvalue being the same as for the original matrix. Thank you.